Here's the problem that we will be working in this video. I am told the coefficient of friction on a rock climber's shoes. And using only friction, we want to know what the steepest slope is the climber can walk up without slipping. So this is going to be an applied Newton's laws problem where we will need to identify our givens, identify what we're looking for, sketch, draw a free body diagram, and probably pick an origin. So this one involves friction and it involves an angle. What are we looking for in this problem? Steepest slope. That is theta, right? That's the angle. All right, let's sketch this, which helps us get kind of our information organized. All right, so I have my climber on the slope. I've identified theta as what I'm looking for. Now I need to ask myself, if the climber were to slip, which way would he go? I'd like you to pause the video now and think about your answer to that. Which way would the climber go if they were to slip? Did you pick down the incline? I hope so. So what we call that is pending motion. So he's not falling, but if he were to fall, that is the direction that he would go. All right, now we want to identify which direction friction is acting. So pause the video and think about your response to that. Which way does friction act? I hope that you picked up the ramp because friction always opposes motion or pending motion. So that's why we thought about that first. Friction has to go in the opposite direction. So friction actually is a force that goes up the hill. Now let's draw our free body diagram. Why don't you pause the video on this one and try to sketch it yourself first before looking at mine. Hopefully yours looks like this, with 3 forces present. Now I need to select an origin for my Cartesian coordinate system. Where should I put it? Certainly I want to put it at the center of my free body diagram, but this is a case where I'm going to rotate it. The reason I am rotating it is notice that when rotated, I have the friction lies right on the x-axis and the normal lies right on the y-axis. And the only force in this diagram that I have to break into components is the weight. That's going to make things a little easier. Now I am sketching the x and y components of the weight. So the components of the weight that lie along the x and y axes, and make a triangle where the weight is the hypotenuse. And I'm going to label my x component of the weight and my y component of the weight, where the x is that part that lies along the x-axis and the y is the part that lies along the y-axis. I'm going to throw my theta in there, where the theta in that little triangle is the same as the angle on the ramp or the hill for my climber. All right, now using my trigonometry and my right triangle, I am going to figure out which trig functions correctly go with which component. So I can see that the weight in the x direction is opposite, so it has sine, and the weight in the y direction, or that component, is adjacent to angle theta, so it has cosine. And I'm going to rearrange each of those, solving for wx and wy. So it'll be just a little bit easier when I need to substitute those into my equation in a moment. Now, let's write Newton's second law in the x and y directions. All right, so the sum of the forces in the x direction, there's a lot on there, so I'm going to highlight my x-axis there, and I have two forces that lie along it. One of them is the force of friction, and it acts in the positive x direction as I've laid out my axes, and the other is the weight in the x direction, and it acts in the negative x direction as I've laid out my axes. And Newton's second law says that all of that has to equal mass times acceleration. My climber is not accelerating, so that equals 0. Now we'll do the same thing, only for the y direction. I'm going to highlight my y's in green. So I'm going to sum up the forces in the y direction. I have the normal that acts in the positive y direction, and I have the y component of the weight, which acts in the negative direction. So that gets a negative sign. So there's the sum of my forces. I have to set that equal to mass times acceleration. The climber is not accelerating in the x direction, so that equals 0. I am going to sub in that weight is m times g, mass times g, into both of those equations. We can calculate friction by using the coefficient of friction multiplied by the normal. So I'm taking that equation and I am replacing force of friction with coefficient of friction multiplied by the normal. Hey, my other equation actually has how to calculate the normal. Let's substitute the value that we got from our second Newton's second law equation into our first one for the normal. Whew, that's a lot of letters, but it's going to clean up fast. Let's note that mass and gravity are in every single term, so we can divide by those and cancel those out. Now, what we'd really like to do is get theta isolated, get theta all by itself. So let's at least get the trig functions on the same side. Do you happen to remember what sine theta over cosine theta equals? Did you answer tangent of theta? If so, that's awesome. Pat yourself on the back. If not, I'm going to show you how you could figure it out if you run into this situation again in physics. Sine theta is opposite over hypotenuse. Cosine theta is adjacent over hypotenuse. I'm going to write them out like that. Now that I've done that, I can see that the hypotenuses are going to cancel out. What I'm left with is opposite over adjacent. And opposite over adjacent is tangent of theta. All right, back to my problem. So I am given the coefficient of friction is 1.4. I'm going to set that equal to tangent of theta. I'm going to take the inverse tangent of both sides. So the inverse tangent of 1.4 should equal theta. Make sure that you have your calculator in degree mode if you're looking to get your answer in degrees. And make sure that you take the inverse tangent, not the tangent.